Now, I think we've established that having no memory management system leaves us with a number of problems. So let's not imagine that that's a realistic choice. Let's try to figure out something that is realistic. What we're going to look for is an abstraction. And this abstraction, this layer of indirection, is what's going to help us to identify how to make this work. And our concept for this is an address space. And an address space is, well, it's a set of addresses that a process can use. Each process has its own address space, independent of that of any other process, except, of course, when we create shared memory. And here's kind of the analogy that I want us to use to think about it, which is it's like telephone numbers. So a typical telephone number in Canada or the United States of America takes the form of number, and then usually for formatting purposes is a dash, and then 4 more numbers. Now maybe you're thinking, wait a minute, that's too few numbers, but hold on with this so far. In theory, any number in the range from 0 to 9 for each digit is going to be a valid number. In practice, certain numbers are reserved, like 3 zeros as the prefix, that first part, or 555. It's used for numbers you see in TV shows because they're not real. They don't actually work. If you try to dial them, it doesn't succeed. But given the number of phones in the combined countries, that's even if we completely filled the address space, that would be 10 million numbers. And we have a population combined of Canada and the USA that exceeds 350 million. That's probably not going to work. Okay, here's the solution. And the solution is area codes, right? In fact, probably you looked at this and you thought, what do you mean phone numbers are 7 digits? They're 10 digits and they always have been. Whether you think 10 digits 10-digit dialing has always been the case is both a question of age and location. That 7-digit dialing was quite common when I was young, and then 10-digit dialing was introduced in the Toronto region at some point. But in other areas of the country, there's kind of been no need, and 10-digit dialing was adopted on a basis of eventually. We'll do that when it becomes necessary. You may imagine if you live in Yukon, it's still not necessary since all the Yukon is covered by this one area code. Nevertheless, 10-digit dialing is common basically everywhere now. When you look at the map, I think you can get a pretty good indication as to why. Okay, so if we look at a number, it's 416-555-1234. It's identifiable by its area code by being located in the Toronto region, or at least it's a cell phone that's registered with that number. There's, of course, a distinct possibility these days that you could, have a number from Ottawa while you live in BC, or vice versa. And presumably, if you look at the area code, 212, it's New York City. And hypothetically, if there still exists a district in North America where 10-digit dialing is not mandatory, if you dial 555-1234, it will basically implicitly add the area code at the front of that, and it connects you to that number in your local area code. So there can be 416-555-1234 and 212-555-1234, and if 7-digit dialing were still allowed, it would just connect you to whichever one it assumes is the local one, and you wouldn't have to worry about it. So what we're actually going to see is letting each process have its own, effectively, area code, right? We're not altering any addresses in memory. We're just going to add a prefix automatically to every memory location. So a process can write to location 1024, and a different process, process 2, can also write to a location 1024, and they're 2 distinct locations in physical memory. Maybe 21024 and 91024, just making up a silly example. So we effectively prefix every memory access with an area code. All right. That's actually really easy. And so now an address that is generated by the CPU, like the 28 in a jump to 28 instruction, that's the logical address. and we add the area code to the front to produce the physical address, the actual location in memory, and that's the address that gets sent over the bus. To make that happen, we need some sort of register that contains the area code and will automatically add it so that everything works out the way that we expect. And in practice, the area code is in a register called the Relocation Register. So when the CPU issues a logical address, it goes into the memory management unit. The memory management unit looks at the relocation register, adds that value to the memory address to produce the physical address, and the physical address goes out over the bus as seen in the diagram. Now listen, in the example that we're talking about here, adding a 2 at the front or a 9 or a 14 at the front or whatever is pretty clean. There's no reason why the relocation register has to be perfectly even. The relocation register could contain a value like 14,222. And if that's the case, then yeah, it's a little harder to see the physical address, but the addition is the same, right? We just made it a little bit simpler by using examples that look pretty. Okay, but given a relocation register, we've actually got some things going for us here. The process itself doesn't know the physical address. It only knows the logical address that it wants to issue, 346, and we get a runtime mapping of variables to their physical memory location. We also get some amount of protection between the processes because basically you can't dial outside your area code, right? We get even more protection if we bring back the base and limit registers, so we compare the physical address to the base and the base plus limit to make sure that we are sort of staying in the right area, but that would actually kind of work. And another thing that we've got is relocation. And we can relocate a process in memory if we change the relocation register's value accordingly. So a process that is currently loaded into memory with a relocation register value of 14,000, you just move all the memory to a new place, you change the value of the relocation register. So in the example that's on here, we change it to the new starting location of 90,000. And after that, the old location of the process memory can be marked as available, and that's it. Another process can use it, and there we go. Okay, there is now some amount of overhead here, right? Every memory access now includes an addition, possibly 2 if a limit register is used to do comparisons. Comparisons are pretty quick for the CPU, but addition can be a little bit slower because of carry propagation time. If you didn't talk about this in hardware, that's basically about the idea like, well, you might have to carry the 1 repeatedly, right? If you have a value that's 99999 and you're adding 1 to it, okay, this is 0, carry the 1, add that, again, carry the 1, and so on and so on. That's actually somewhat annoying. If you're the sort of person who hasn't thought much about the hardware stuff and you've been wondering why your educational program at the university has made you learn some details about hardware, this is an example of why. You've noticed in the section that we've asked hardware developers to bail us out of various problems by taking operations that would be slow and doing them as a hardware operation, which is fast. This is a mutually beneficial relationship. A friend of mine who's a hardware person was constantly saying it's really nice that whenever we manufacture a chip that has a defect in it or something, we can work around it in software by doing some extra addition or multiplication or something like that. So it is beneficial. But I think you may be getting a hint as to why we need to talk about the hardware stuff because, well, if you don't understand the hardware, the software you write may be slow, and you might not have an understanding of why. So, anyway, digression aside, we do have a penalty associated with doing this additional step, but it does allow us to do more stuff in parallel. So, sharing memory without being so worried about people messing up the memory of others is good. So, we're usually going to say it's worth it. We'll take it. Let's also talk about swapping. So to run, a process has to be in memory, and given enough processes, or at least sufficiently demanding processes, it won't be possible to keep them all in memory at the same time. And a process that is blocked is taking up memory, but it might be logical to make some room for processes that are currently ready to run. And the the process, if you will, of moving a process from memory to disk or vice versa is called swapping. And this diagram shows a pretty good idea of what it's like. Main memory, some of it is dedicated to the operating system, to the kernel, so that stuff is going to stay. But the operating system can and will choose to move other processes in and out of memory as it sees fit. And swapping out is what we call it when some data is moved to the backing store, usually the hard disk drive, and swapping in is what happens when it comes from that location into memory. And unfortunately, swapping a process to disk is quite painful. If the process is using 1 gigabyte of memory to swap another process to disk, we need to write 1 gigabyte of data to disk, and to load it back, again, we have to read that 1 gigabyte again. And if 1 gigabyte strikes you as being totally ridiculous in size, at least according to the Mac OS system utilities, with 5 PDF documents open when I wrote this, where the combined size of the files is 80.6 megabytes, the preview application consumes 2 gigabytes of memory. Why? Good question. That's not the point. The point is that that's a lot of data, and we would only like to swap it if we absolutely have to. Now, most operating systems don't actually do that in practice because it's too slow. Too much time would be wasted swapping processes to and from disk. A modified form of swapping is used, but we're going to talk about that a little bit later on in memory because we're still building our way up to that. The other thing to note is that when we swap a process back in from disk, we don't have to put it back in exactly the same location where it was before because, well, we can just use the relocation register, right? And this diagram shows a progression of swapping some stuff around in memory where process A is in memory, then we add B, then we add C. Process A is swapped to disk, process D comes in, and then to make room for process A to return, we're going to swap B out, and in the final step we have C, A, and D all in memory such that everything is happy, right? And to do this, again, we just operate using things we've already discussed. We need to update the relocation register when we've changed the location of A, but otherwise we can make this happen. Okay, now here's the thing. Thus far, we've talked about process memory as if it is large, fixed size, and just a big block, right? In this previous diagram, A gets a nice big rectangle of memory. That's probably not true, right? From previous programming experience, when you use the new keyword or malloc or something like that, you get more memory. Now, you don't have a fixed size block that you play with, and you deal with this limitation. You can just request more memory. Now listen, you might not get it. If you ask for a ridiculous amount of memory, the operating system might not be able to fulfill that request, but surely the idea of dynamic memory allocation must exist. And so that's what we're going to talk about in our next topic. We're going to think about dynamic memory allocation as opposed to thinking of just big blocks.